STEM Hub. Engineering concepts made simple.
All right, so this particular question has is two spring. So this question wants us to understand how adding more springs to a set of system in vibration affects either the frequency and how the frequency also have effect on the K that we get. So in this place, we are going to be looking at a spring coefficient. We are going to look at different spring, how to get the equivalent spring in a system. So a spring's mass system, it has a spring constant of K1, mass of M1, and a natural frequency F1. If a second spring K2 is added in series with the first spring, the natural frequency is half of F1. So I said determine K2 in terms of K1. So initially we have a spring of this system. So what we said is that a spring mass system having K1, M, and has a natural frequency. So this is what we have. A single degree of freedom problem, just one mass, one spring. Then your natural frequency, let's name it F1 for the first situation. So you know that for this F1, from our standard formula, we know that it's 1 over 2 pi square root of K1 over M. That's what we have. So we equate this to F1, just as we stated here. So now the question now says if a second spring K2 is added in series. So you series two of the spring. So let's say the second spring that was added is K2 and we have a mass M. The mass is not changing. So we're adding a second spring. Now, due to this addition of spring, the natural frequency is now reduced, or the natural frequency now becomes half of the first initial frequency. So what do? So now that for this system of springs, our frequency is half of F1 that we initially have. So when two springs are in series, we have 1 over K equivalent equals to 1 over K1, which is for the first spring and the second spring. So upon looking for the LCM of both, so we are going to be having K1, K2, then you have your K2 plus K1 equals to 1 over KEQ. So this is what, inverse of this is what gives us this. So with this, we know that Fn2, which is supposed to be half of F1, when we have just K1, is 1 over 2 pi. The Q now will be the Q equivalent over M, which is same thing as F1 over 2. So now, initially, we stated that F1 equals to half square root of K1 over M. We know that the formula for F is equals to 1 over 2 pi square root of K over M. That's initially the formula for F, natural frequency. So we know that's the formula for F1. We know that F2 is F1 over 2, which is also K equivalent over M. And we obtain K equivalent to be K1, K2 all over K1 plus K2M. So now I know that my F1 is initially this. So I bring it here. What we have here, I bring it here. So these two here can cut out the first two, just as we initially stated. So 1 over 2 pi, which is F1. So I'll bring these two here. 2 cancels 2. I have 1 over pi. This is my F1 as we initially have. So pi cancels pi. Then I square both sides. This square root goes out. I have 1 over 4. Square of 2 is 4. So 1 over 4. K1 over M. Then we have what we have in the square root. So K1 takes out K1. We have 1 over 4 equals to K2, on bracket K1 plus K2M. Now, when we have this, we multiply K2 by 4. We have 4K2 equals to K1 plus K2. Now, 4K2, upon analysis, we have 3K2 equals to K1. So we can say, conversely, that K2 equals to K1 over 3. So just as the question stated that we should get the relations between K1 and K2. In the next question, we are going to be looking at a series of systems whereby we talk about how the masses are changing and also the addition of new masses and how it affects the total answer. Thank you very much.